Let's give a quick recap of what we've seen so far. We took for granted that SAT is NP-complete. This means that all the problems in the class NP can be reduced to SAT. So if we can solve SAT in polynomial time, then we can solve any problem in NP in polynomial time. Then we saw that 3SAT is NP-complete. This involved a reduction from SAT to 3SAT. Then we proved that the independent set problem is NP-complete. This involved a reduction from 3SAT to the independent set problem. This was a quite interesting reduction because it involved a transformation from a logic problem, 3SAT, to a graph problem, independent set problem. Then we proved that the clique problem and vertex cover problems were NP-complete. These involve more trivial reductions from the independent set problem. What we're going to do now is we're going to prove that the knapsack problem is NP-complete. As an intermediate step, we're going to look at the subset sum problem. We're going to prove that the subset sum problem is NP-complete. This is going to involve a reduction from the 3SAT problem to subset sum problem. This again is a quite non-trivial reduction because it involves transforming a logic problem, 3SAT, into this optimization problem, subset sum. Once we prove that subset sum is NP-complete, it'll be quite easy to prove that the knapsack problem is NP-complete. We'll leave this last step as a homework problem, proving that knapsack is NP-complete once we know that subset sum is NP-complete. If you recall from the beginning of the course, we studied dynamic programming algorithm for the knapsack problem. And there we saw an order n times b time algorithm for the knapsack problem. Now we pointed out why this is not polynomial time, why this running time is not polynomial in the input size. In order to be polynomial in the input size, it has to be polynomial in an n and log of b. Why this is not polynomial is somewhat of a subtle point. I think it becomes much clearer when you see this reduction from 3SAT to subset sum or 3SAT to knapsack. What you'll see in this reduction is that capital B will be exponential in the size of the input formula for the 3SAT problem. So if we use this algorithm to solve 3SAT, this would give us an exponential time algorithm for 3SAT. It's a quite clever reduction, so let's dive into it. Let's prove that the subset sum problem is NP-complete. Let's start with the definition of the subset sum problem. The input to the subset sum problem are n positive integers, which we'll denote as a1 through an, and one additional integer, t. Our goal is to find a subset of numbers which sum up to exactly t. So we want the sum over the indices in this subset of the corresponding numbers to be equal to exactly t. We output such a subset if it exists, and otherwise we output no. This is a great practice problem for dynamic programming. Using dynamic programming, we can solve this problem in order n times t time. If you want practice with dynamic programming, I suggest you try that. Let's take for granted that there's an order n times t time algorithm for the subset sum problem. Now, given that fact, the subset sum problem is known to be in the class P. Is that true or false? This is false. Just like with the knapsack problem, this is not polynomial in the input size. To be polynomial in the input size, the running time would have to be n times polynomial in log t. We're going to prove now that the subset sum problem is NP-complete. Again, there are two parts to the proof. First, we have to prove that the subset sum problem is in the class NP. So we take an input instance to the subset sum problem. This is specified by n numbers, a1 through an, and t. And we take a proposed solution, s. Then we check that the sum over the integers in that subset equals exactly t. How long does it take to compute this sum? Well, there is the most n numbers there, so there's order n time. And then how long is each number? Well, each number is at most log t bits. So to sum these up, takes at most order n times log t time. Notice this is polynomial in the input size, so we can verify solutions in polynomial time. Next, we have to show that the subset sum problem is at least as hard as every problem in the class NP. So we have to take a known NP-complete problem and reduce it to the subset sum problem. Which problem do we choose? Well, we're going to choose the 3SAT problem, and we're going to reduce it to the subset sum problem. The reduction is very clever and somewhat involved, but it doesn't involve any heavy math or anything like that. And it really illustrates why the order n times t time algorithm is not efficient for this subset sum problem. The input to the subset sum problem will consist of 2n plus 2m plus 1 numbers. There are n variables and 2n literals, so we'll have a number for each literal. There are m clauses, so we'll have 2 numbers for each clause. And then we'll have one additional number, which is our desired sum. We'll have v1 and v1 prime corresponding to x1 and x1 bar. v2 and v2 prime for x2 and x2 bar, and vn and vn prime for xn and xn bar. We'll have these 2 additional numbers for the first clause, and so on for the m clauses. And finally, we'll have the desired sum. Now these numbers are all huge. They're going to be at most n plus m digits long. And we're going to work in base 10. This is so that if we add up any subset of numbers, there'll be no carries between the digits. Note these numbers are huge. For instance, t is on the order of 10 to the n plus m. This illustrates why our order n times t algorithm is a somewhat terrible algorithm. Now let's take a look at the actual specification of the input to the subset sum problem. Let's start with these numbers corresponding to the two n literals. In particular, vi corresponds to xi. So we're going to include this number vi in the subset S if and only if the literal xi is set to true. Similarly, vi prime corresponds to xi bar, and we'll include vi prime in the subset S if and only if the variable xi is set to false. An assignment for the 3-sat formula either sets xi to true or xi to false. Therefore, we need for the subset sum problem that either we include vi in S or vi prime in S. But we can't include both, and we can't include neither, because then we don't know how to set xi. So we need to ensure that exactly one of vi or vi prime is in S. How do we achieve this? Well, in the ith digit of these three numbers, vi, vi prime, and t, we put a 1. In all other numbers, we put a 0 in the ith digit. Now, by using base 10, we'll ensure that there's no carries between the digits, so each digit is going to behave independently of each other. Recall that t is our desired sum, so the only way to achieve a desired sum that has a 1 in the ith digit is to include either vi or vi prime in S, but not both and not neither. So this specification ensures that our solution to the subset sum problem is going to correspond to an assignment. Whether it's satisfying or not is another issue. But for now, at least we know that we have an assignment. So either we're going to correspond to xi being set to true or xi being set to false. To illustrate the reduction, it'll be useful to have a running example, and we can fill in the numbers as we go along. So let's consider this input formula to the 3-sat problem. It consists of 3 variables and 4 clauses. For variable x1, there'll be 2 numbers, v1 and v1 prime. Similarly, for x2, there'll be v2 and v2 prime, and for x3, there'll be v3 and v3 prime. In addition, there'll be 2 numbers for each clause. So we'll have S1 and S1 prime for clause 1, S2 and S2 prime for clause 2, S3, S3 prime, S4, S4 prime for the last 2 clauses. And finally, we have T, which is our desired sum. These 15 numbers specify the input to the subset sum problem. These numbers are going to be 7 digits long. The digits correspond to the variables, 3 variables, and clauses, 4 clauses. The first 3 digits correspond to the 3 variables, x1, x2, x3. The next 4 digits correspond to the 4 clauses. Now an assignment to F either sets x1 to true or false, so we wanted that a subset sum solution either includes v1 or v1 prime in the subset. How did we ensure that? We put a 1 in the first digit for v1, v1 prime, and t. For all other numbers, we put a 0 in the first digit. Now, assuming there's no carry from the other digits, how can our subset of numbers achieve a sum of 1 in the first digit? Well, the only way is to include either v1 or v1 prime, but not both and not neither. So we have to include exactly one of these two in order to achieve a sum of 1 in the first digit. Similarly, we put a 1 in the second digit for v2 and v2 prime and for t. And in the third digit, we put a 1 for v3, v3 prime, and t. And we put a 0 for all other numbers in the second and third digits. This ensures that exactly one of v2 and v2 prime is in the subset, and exactly one of v3 and v3 prime is in the solution to the subset sum problem. So now we know that any solution to the subset sum problem corresponds to an assignment. Now we have to ensure that it corresponds to a satisfying assignment. So for that, we use these remaining 4 digits. The first n digits correspond to the variables, so the next m digits correspond to the clauses. So digit n plus j is going to correspond to clause cj. If the literal xi appears in the clause cj, well, xi, this literal, corresponds to this number vi. So we're going to put a 1 in digit n plus j for this number vi. Similarly, if the literal xi bar appears in this clause, well, in this case, this literal xi bar corresponds to this number vi prime. So we put a 1 in digit n plus j for this number vi prime. What this does is it encodes the clauses in these numbers vi and vi prime. Let's go back to our running example. Our first clause contains x1 bar, x2 bar, and x3 bar. This clause corresponds to the fourth digit, so we're going to put a 1 in v1 prime. We put a 1 in v2 prime, and a 1 in v3 prime. Similarly, for the second clause, we put a 1 in v1 prime for x1 bar, v2 prime, and v3. For clause 3, we put a 1 in v1, v2 prime, and v3. Clause 4, v1, and v2. Now for the first clause, we want to ensure that either v1 prime, v2 prime, or v3 prime are included in the subset in the solution to the subset sum problem. We just need that at least one of these is included. We don't need that exactly one, so we can't just put a 1 here in t. We want that either 1, 2, or 3 of these numbers are included in the solution. So we put a 3 in the fourth digit of t, fifth digit, sixth digit, and seventh digit. Now if we include all 3 of these numbers in our solution, then we're okay. But what if we only include one of these digits? What if only one of these literals is satisfied? Well, that's where we use these buffer numbers, s1 and s1 prime. We're going to put a 1 in the fourth digit for these two numbers. The point is that if only one of these 3 literals is satisfied, then we get up to sum of a 3 by including both of these buffer numbers. So we get a 1 from one of these 3, plus 1, and that gives us 3. What if all 3 of these literals are satisfied? Then we don't have to use either of these buffer numbers. What if exactly 2 of these literals are satisfied? Then we use one or the other of these buffer numbers. But if none of these literals are satisfied, then using both of the buffer numbers only gets us up to a sum of 2, so we can't satisfy t. We can't get a solution to the subset sum problem. The only way to get a solution to the subset sum problem is to have at least one of these literals satisfied, and then we can use the buffer numbers to get the desired sum in this digit. So similarly, for clause 2, we put a 1 in this digit for s2 and s2 prime, s3, s3 prime, s4, and s4 prime. All the other numbers have zeros in these digits. This specifies the reduction from the 3-stat formula to the subset sum problem. Note that v1 is the number 1,011,011. v1 prime is the number 1,001,100. s4 and s4 prime are the numbers 1. t is the number 1,113,333. Let's go back and specify the remainder of the reduction in general. For each clause, we encoded the literals which appear in that clause, using vi and vi prime. To ensure that at least one of these literals is satisfied, we put a 3 in digit n plus j of t. Then if all of the literals in this clause are satisfied, we get the desired sum in this digit. What if only 1 or 2 of the literals in this clause are satisfied? How do we get the desired sum? Well, that's where we use sj and sj prime to act as buffers. We put a 1 in digit n plus j of both of these numbers. And finally, we put a 0 in digit n plus j of all the other numbers which we haven't specified so far. The main point is that if all 3 of the literals in this clause are satisfied, then we get the desired sum of 3 in this digit. If exactly 1 or 2 of these literals are satisfied, then using these buffer numbers, we get the desired sum of 3 in this digit. But if none of the literals in this clause are satisfied, then there's no way to achieve a sum of 3 in this digit, because the sum of these buffer numbers only adds up to 2. What we've sketched so far and what we'll formally prove now is that the subset sum instance that we constructed has a solution if and only if the original 3-stat input is satisfiable. This is going to prove that we did a valid reduction. Let's start with the forward direction. Let's take a solution S to this subset sum instance. So we know that if we sum up the numbers in S, it sums up to exactly t. Let's first look at the first n digits. These correspond to the n variables, x1 through xn. We know that t has 1 in digit I. In order to get a 1 in digit I, we have to include vi or vi prime in our subset S, but not both. If we include both, we get a 2 in digit I. And if we include neither, we get a sum of 0 in digit I. So the only way to get a sum of exactly 1 in digit I is to include exactly 1 of vi and vi prime. If we include vi in our subset S, then we set the variable xi to true. If we include vi prime in our subset S, then we set the variable xi to false. So from this solution to the subset sum problem, we get an assignment. We get a true-false assignment for the variables. Why is this a satisfying assignment? Well, to see that, we'll look at the remaining digits. We just saw if we take a solution to the subset sum instances that we specified, then using the first n digits, that specifies a true-false assignment for the n variables, x1 through xn. Now, using the remaining m digits, we're going to show that that assignment that we just specified corresponds to a satisfying assignment. It satisfies the input formula f. The first n digits correspond to the variables. The next m digits correspond to the clauses. So let's look at digit n plus j, where j varies between 1 and m. So digit n plus j corresponds to clause cj. In our definition of the subset sum instance, we put a 3 in digit n plus j of t. So we need to achieve a sum of 3 in digit n plus j. In order to get a sum of 3 in digit n plus j, we have to include at least one of the numbers corresponding to the literal appearing in clause cj. If we satisfy exactly one literal in cj, then we use both sj and sj prime as buffer numbers, and then we get a sum of 3. If we satisfy exactly two literals in this clause, then we either include sj or sj prime in our subset S, and that gives us a sum of 3. If we satisfy exactly 3 literals in this clause, then we don't need to use either of these buffer numbers, sj or sj prime. Just using these 3 satisfied literals gives us a sum of 3 in this digit n plus j. If we satisfy 0 of the literals in this clause, then there's no way to achieve a sum of 3 in this digit, and therefore we don't have a solution to the subset sum problem. We're assuming we have a solution, therefore we must have at least one satisfied literal in this clause. Thus, cj is satisfied, and thus every clause is satisfied, and therefore we have a satisfying assignment for f. So we've shown that a solution to the subset sum instance corresponds to a satisfying assignment for a 3-sat formula. And we've actually shown how to transform this solution to the subset sum problem to find the satisfying assignment to the 3-sat formula. Now let's prove the reverse implication. Let's prove that if we have a satisfying assignment for this 3-sat formula, it corresponds to the solution to this subset sum problem. Let's prove the reverse implication, that a satisfying assignment for the 3-sat formula corresponds to a solution to the subset sum instance. So let's take a satisfying assignment for f, and we'll construct a solution to the subset sum instance in the following manner. In our satisfying assignment, if we set the variable xi to true, then we add the number vi to the solution s. And if we set the variable xi to false in our satisfying assignment, then we add the number vi prime to our solution s. We're adding exactly one of vi and vi prime to s. This means in the ith digit we get exactly 1. So the ith digit of t is correct. Now let's look at the jth clause. We started from a satisfying assignment. Therefore, at least one of the literals in this clause is satisfied. The numbers corresponding to these literals give us a sum of 1, 2, or 3 in the digit n plus j. T has 3 in digit n plus j. So how do we achieve a sum of 3 in digit n plus j? Well, using the numbers corresponding to these literals, we get a sum of 1, 2, or 3. And then we can use sj and or sj prime to get up to a sum of 3. This ensures that digit n plus j is correct, and therefore the last m digits are correct, and the first n digits are correct, and therefore we have a solution to the subset sum instance. So we've proved this equivalence, and we've proved that our reduction is correct. We just proved that the subset sum problem is NP complete. Now a nice homework problem is to use that fact that subset sum problem is NP complete, and then prove that the knapsack problem is NP complete. And make sure that you use the correct version of the knapsack problem, the version which lies in the class NP. Now to prove that the knapsack problem, or any problem, is NP complete, there's 2 parts. You first have to prove that the desired problem lies in the class NP, and second, you have to take a known NP complete problem, and you have to reduce the known NP complete problem to this new problem, in this case, knapsack problem. We know that all problems in NP reduce to this known NP complete problem. Therefore, if we show a reduction from this known NP complete problem to the knapsack problem, then we know that all problems in NP reduce to the knapsack problem. Now, which problem are you going to use for this part? Well, I'm not trying to trick you. So what you're going to use is the problem that looks most similar to the knapsack problem. In this case, it's a subset sum problem. On the homework or exam, if you have a graph problem which you're trying to prove is NP complete, what are you going to use here? Probably a graph problem which sounds similar or looks similar to the desired problem. If you have a logic problem you're trying to prove is NP complete, then probably going to use SAT or 3-SAT over here. The other thing to make sure of is that you're doing the reduction in the correct direction. So you're assuming you have a polynomial time algorithm for this problem, and you're using that to solve this problem in polynomial time. So you have to take an input to this known NP-complete problem and reduce it, transform it into an input for this problem. Then if you take a solution to this problem, then you can transform it back to a solution to this original problem. So you have to transform inputs from this known NP-complete problem to inputs to this new problem. That's a common mistake that students make. Even though they write the direction this way, they actually do the reduction in the other direction. They take inputs for this problem and transform it to inputs to this problem. You have to make sure you're doing it the correct direction. So you take inputs to the known NP-complete problem and transform it to inputs to this new problem.